I'd like to talk through solving a problem involving conservation of angular momentum and a high diver. The problem goes like this. A high diver is jumping off a cliff into the water below. And when he first jumps off, he's in a laid out position and starts doing a few flips end over end. But about halfway down, he pulls himself into a small ball and changes his spinning rate right before he hits into the water. There's a few details about the diver that we know. He's 6 feet tall, he weighs 170 pounds, and when he tucks himself into a tiny little ball down here, the diameter of his tucked position is around 30 inches. So that's what we got to work with. The goal is to start with his angular rate of rotation of 1 revolution per second, figure out how fast he's going when he tucks himself into a small ball. I wonder if you can think about this first, like what do you think will happen? Most everybody's intuition is correct, that when he pulls himself into a small ball, he ends up spinning faster. But this would be predicted by both conservation of angular momentum, because when he's into a small ball configuration, his moment of inertia is less than when he's in the spread out configuration. So if angular momentum is conserved, a lower moment of inertia means a higher rate of spin, because angular momentum is I times omega. But it's also predicted by kinetic energy. Kinetic energy is 1/2 I omega squared for a spinning object. And if the moment of inertia when he's in the laid out position is higher than when he's in the curled up position, that would also predict a faster rate of spin. And probably it's difficult to tell at the outset when you first start studying energy and angular momentum which is conserved. So I'll just go ahead and tell you the answer to part A, which you can read. That is that it's certainly angular momentum that's conserved, and probably not rotational kinetic energy. That'll be true for most spinning things. Your go-to conservation law is conservation of angular momentum when things are spinning. And remember that angular momentum is conserved whenever the net external torque is 0. So nothing he can do to himself can apply a force on himself to make him spin faster or slower. He can change his shape, but he can't add an external torque to speed him up or slow him down. Now I would like to say one other thing. I mean, it's true, as he goes, gravity is going to pull him down faster and faster and faster. So his linear speed is going to increase. That's governed by conservation of energy. But the force of gravity, which acts on his center of mass, also can't make him spin faster or slower. So the work done by gravity makes him go faster because he's in free fall, but any change to his rotation rate, well, there can't be any external forces that do that. So the external torque is 0 and angular momentum is conserved. So if you want to write something about that, that'd be great. Now parts B and C of this example ask you to calculate the moment of inertia of the diver in each of his shapes. Here when he's spread out and here when he's curled up. So I think if you want angular momentum in SI units, you're going to realize almost immediately that we have to take care of some units things here. We have his length, but it's in feet and inches. We have his weight in pounds, when really we would like his mass in kilograms. And we have the diameter of his body, but probably we're going to need the radius of the ball that he's curled up in, and that's also going to have to be in meters. So the first step for you is to calculate his mass, his length when he's in the stretched out position, and his radius when he's in the curled up position. So his length is how long he is here, and his radius is half the diameter down here. So how about you pause the video and look up the various conversions and see if you can work it out. Because I already did, and I got 77.3 kilograms for his mass. And for his height or his length, I got 1.83 meters. and for his radius, when he's all curled up in the ball, just 0.38 meters. So the next thing we have to do is figure out which of the formulas from table 9.2 best approximate his shape. Well, when he's in this configuration here, all stretched out, flipping end over end, he's really kind of like a slender rod. Now if you look in the table, you'll see that there are some entries for like door-shaped things, slabs, but none of them have an axis of rotation that have them spinning end over end. So we have to use the slender rod formula for moment of inertia. And that is that the moment of inertia of a slender rod is a 12th ml squared. And when he's curled up in a ball, if we use ball as an appropriate metaphor for his shape, he's going to be like a solid ball. So the moment of inertia of a solid ball is 2/5 mr squared, if you look that up in table 2. So what's left for you to do is to calculate these things in SI units. So you could pause the video here and see what you get, but I get 21.6 kilogram meter squared, which are the SI units of moment of inertia. And I only get 4.46 for his moment of inertia when he's curled up in a ball. And that's the reason why he ends up going a little bit faster, because his moment of inertia is less, but the product of I times omega has to be a constant. So we've done parts B and C, and we need to take a look at parts D and E. Let's take a look at part D here. It's pretty straightforward. If we're going to say that angular momentum is conserved, the mathematical embodiment of that is angular momentum after, I always use the prime variables for that, has to equal angular momentum before. And for a rigid rotator, the angular momentum is I omega. Which you can solve for the final angular speed. So at this point, you could pause the video and work out an answer yourself. I'm going to write it down in just a minute, but I do want to point something out about units that's important to keep in mind. When you're using any of these conservation laws, you can use any units you want. So you don't have to convert omega into radians per second. You could work with the revolutions per second that was given up there. You could convert to radians per second if you want, but for a conservation law, you don't need to. You just have to use a consistent set of units. The only time you need to use SI units is when you're asked to render an answer to a question about kinetic energy or angular momentum in SI units. In any case, to 2 sig figs, I find that he's rotating pretty quickly, 4.8 revolutions per second, if you use 1 revolution per second as his starting angular speed. That's pretty fast. If you stop and think about it, he'd be flipping over head over heels 5 times per second. Probably get pretty dizzy if you did that. So the last part of the question is to figure out how does the kinetic energy after compare to the kinetic energy before. Specifically, we started with saying angular momentum was the same. Let's check what the change in kinetic energy is. And the way we're going to get that is take a rotational kinetic energy final and subtract the initial rotational kinetic energy. And the formula for rotational kinetic energy is 1/2 I omega squared. So it's just a matter of plugging and chugging numbers, but I do have to tell you that since you're calculating kinetic energies and you want the answers in joules, here for omega you do have to use radians per second. And it's not too hard to convert revolutions per second into radians per second, because there are 2 pi radians in a revolution. So you just have to take the angular speeds that you have, multiply them by 2 pi, and then don't forget to square them, and also don't forget to use the moment of inertia afterwards and the moment of inertia before. If you calculate this out, I think you get around 20-30 joules for the kinetic energy afterwards, and just about 430 joules before. So if you subtract these two, you end up with something on the order of 1600 joules. And it's also important to note that that comes out positive. So when he pulls himself into a ball, he ends up with more kinetic energy than he had when he started. And it's an interesting question to ask and answer, where did this energy come from? It didn't come from gravity because that doesn't exert a torque. And he's evidently not able to speed himself up or slow himself down because he can't exert a force on himself from the outside. It turns out it has to do with centripetal acceleration. Think about what would happen if he was spinning at 4.8 revolutions per second and he passed out and his body went limp. If his body went limp and all of his muscles relaxed, he would be stretched back out into the layout position because of the inertia of all the parts of his body that will like them to move in the biggest circle possible. So when he pulls his arms and legs in to form a ball, he does work on himself, as a matter of fact. It takes energy to pull your arms in against the inertia that they have of moving in a circle. And that work that you do, pulling your arms and your legs in, shows up in an increase in kinetic energy. So you can copy these answers down, or I'll post this solution also on Blackboard for you to look at. But it's a good example of conservation of angular momentum and how does kinetic energy change for things that are freely rotating.